All right, we'll get started then, and let's take a look here. So on Friday we were talking about the Metropolis algorithm for the case of somebody visiting islands, right? So all right, let me have you guys settle down, and we're gonna start. Okay, so we're gonna visit islands. We say we got islands 1, 2, 3, 4, 5, 6, and 7. And this was our algorithm, the Metropolis algorithm. Islands, and this was like we start island theta, and then we propose either theta plus 1. So if this if we get heads, so that this is with probability equal to 0.5, or island theta minus 1, we get tails with probability 0.5, right? We start at island, we flip a coin, and we propose either the island above or the island below, okay? And then we check the island, we check the population of the island, and if the proposed island has a greater population, we go for sure. Fix something here. And if not, we will go with probability equal to the population of the proposed divided by the population of the current island. Okay, and if we reject the current island, or I mean, if we reject the proposed island, we stay at the current island one more time. Okay, so our diagram, we can transition from from any island to the adjacent islands. From island okay. All right, and this is kind of where we left off on Friday, and we started calculating out a transition matrix and things like that, right? And the idea is, what we want is and I told you that if we use this, then we'll the stationary distribution of our chain will be equal to our target distribution, okay? And remember, our target distribution is equal to our population distribution, where basically the populations is proportional to the island number, okay? And you know, make sure you do your reading from the textbook. Okay. All right. And so you know, we want a target distribution. We want the stationary distribution of our chain to equal our target distribution. And basically we achieve the stationary distribution when the number leaving a state is equal to the number entering the state. And further, we can say, well, let's just take a look at our island example, and let's just look at one of the islands, okay? So, you know, I said, if we follow those rules for, you know, how the politician should go visit the islands, eventually, you know, we'll visit the islands according to the target distribution, okay? But let's just kind of investigate, all right? Let's see. Let's take a closer look. At one of the islands. All right, so let's do island 4. Okay, and we'll say we will be at equilibrium basically if the number going from island 4 to island 3 is equal to the number going from island 3 to island 4. Sorry. Number island 4 going to island 3 is equal to the number going from island 3 to island 4. And then also, if I'm going to say number from 5 going to, or I'll say number from 4 going to 5 is equal to the number of 5 going to 4. Okay, is that all right? So we want to make sure that the number going away is equal to the number coming in, and if that's the case for basically all the islands, then we're at equilibrium. But let's just take a look at island 4. Okay, so we'll say and we'll note that if we look at the population of island 4 is basically proportional. The population of island 4 is say 4 million or whatever, but this is also proportional. The probability of being at island 4 is just going to be equal to the population of island 4 divided by the total population, right? So basically the population is proportional to the probability. And that's going to be the case for all of the islands, because the total population is the same for everybody. Okay. All right, so let's look at what proportion will go from island 4 to island 3. Okay, or how many go from island 4 to island 3. So number of 4 to 3, this is going to equal basically the population of 4 times the transition probability of 4 to 3. Okay. What is the transition probability of going from island 4 to island 3? Well, first we have to flip tails. And then if we flip tails, then we go with probability of 3 over 4. Is that right? Just want to make sure that that's okay with everybody. So this will be equal to, first we have to flip tails with probability 0.5, and then we will go with probability 3/4 or I'll just leave it at 3/4, okay? Or 0.75. And this is the probability of population 4, so I'll just do P of 4. And so here I have 0.375 times population of island 4. Is that okay? Does that make sense? So this is the number of people going from island 4 to island 3 is equal to the population of island 4 times the transition probability of going from island 4 to going to island 3. Okay. All right, and then let's just take a look at the number of going from island 3 to island 4. Okay, and this will be equal to the population of 3 times the transition probability of going from island 3 to island 4. What's the transition probability of going from island 3 to island 4? What has to happen in order to go from island 3 to island 4? We have to flip heads, right? And if we flip heads and we propose island 4, we are for sure going to go, right? So this will be probability of flipping heads and then we go for sure, so 1. So this is going to just be 0.5. And so this will be probability of being on island 3 times 0.5, and we have 0.5 times 3, okay? So this, we have equilibrium when these two are equal. When 0.375 times probability 4 is equal to 0.5 times probability 3, or basically if island 3 is 3/4 the population of island 4. I just want to make sure this is okay. All right, so let me just transition. Okay, so we have equilibrium when 0.375 times probability of 4 is equal to 0.5 times the probability of 3, or when 0.75 times probability of 4 is equal to 0.3. So when probability of 3 is equal to is 3/4 of probability 4, okay? And then if we look at basically the number going from 4 to 5 and the number going from 5 to 4, we will see the same relationship, okay? So we could say the number going from 4 to 5 is going to be the population of 4 times the transition of going from 4 to 5, okay? So this is going to be 4 times, first we have to flip heads, and then we'll go. So this will be, because we 0.5 times 1, right? So we go for sure. If we propose island 5, so this will be 0.5 times probability of 4. And then over here, this will be the population of 5 times the transition of going from 5 to 4. So this will be the population of island 5. And in order to transition from 5 to 4, we have to flip tails. And then we go with probability 4/5. So this will be probability 5 times 0.5 times 0.8. This will be 0.4 in terms of probability of 5. And what we see is that we have equilibrium when P of 4 is equal to 0.8 of the probability of 5, okay? So now we're establishing kind of a relationship, and so at least for island 4, so we will have equilibrium when island 3 is 0.75 of island 4, and island 4 is 0.8 of island 5. Okay, so this is achieved when island 3 has a population of 3, island 4 has a population of 4, and island 5 has a population of 5. Okay, and this was just one island, and we could explore it for all the islands in our chain, and we could see that if this is our transition probability, okay, if we've determined our transition probabilities this way, then we will achieve stationarity. Okay, the stationary distribution is equal to our target distribution. Does that make sense? Okay, and according to kind of like the Markov theorem, the ergodic theory is that if the Markov chain is aperiodic and is irreducible, and you let the chain run long enough, then eventually the chain will reach its stationary distribution. And when we reach our stationary distribution, and our stationary distribution is equal to our target distribution, then we are drawing values from our target distribution. All right. Are there questions on this? Okay, so let me generalize this to just the Metropolis algorithm. Okay, so this was the Metropolis algorithm applied to a discrete distribution with islands, and our proposal was a coin flip. But this is kind of our, let me generalize it, okay? So, the island example is the Metropolis algorithm applied to a discrete distribution and our proposal distribution is a coin flip. Okay, so let me just do kind of the general Metropolis algorithm. Okay, so we'll say at time k, okay, our current value is x sub k. And then we have a proposal distribution q. Okay, and what we will do is we propose x prime by drawing a random value from Q conditioned on xk. So basically we have x prime coming from Q given x sub k. Right? So we propose some value x prime by drawing a random value from a proposal distribution Q conditioned to add our current value. Okay. So in the island example, let me just, all right, so xk would be equal to theta, our current island. In Q, basically, would either be propose theta plus 1 with probability 0.5, or propose theta minus 1 with probability 0.5. So that's the proposal distribution there. Okay. You could have like a normal distribution proposal. This is a very common choice. And basically, you would say x prime would come from a normal distribution where you set your mean equal to your current x sub k. So you say, centered at x sub k, my current value, I'm going to propose a value drawn from the normal distribution with, you know, some standard deviation sigma. Okay, so here we propose a new value, x prime, drawn from a normal distribution centered at xk. All right. Now the proposal distribution does not have to be the normal distribution. It can be any distribution. Excuse me. Okay, and for it to be the Metropolis algorithm, it just has to be symmetric. Okay, that's the only rule for the Metropolis algorithm. But is this okay? And I guess we can look at the Metropolis Hastings probably on Wednesday. Okay, so for the Metropolis algorithm, the proposal distribution needs to be symmetric in that the probability of proposing x prime given xk is equal to the probability of getting xk if you are at x prime. So it's kind of like, so the normal distribution works because basically the probability of proposing 1 if we are at xk equal to 0 is the same as proposing 0 if we are at xk equal to 1. So that's the requirement for the Metropolis algorithm, is that your proposal distribution has to be symmetric. Okay. All right. So then you have a proposed value. So we have with your proposed values, you will either accept or reject the proposed value. Okay. You accept with probability equal to the minimum of 1 times, or probability of x prime divided by probability of xk, right? So P is the target density, your PDF. And so probability of x prime divided by probability of xk is basically the ratio between the proposed probability, proposed values probability, and the current values probability. Okay, the minimum of 1 and this make sure that if the ratio is bigger than 1, you're not going to have a probability greater than 1, okay? Okay, does that make sense? So here we're just kind of formally defining our Metropolis algorithm. You know, instead of having just the island example and the coin flips and wandering around, now we're saying we will propose values, and this time the values we propose can come from a continuous distribution rather than a discrete one. Okay, in the island case, we had a discrete proposal. You either flip a coin and you go 1 up or 1 down. Now we're saying you have a normal proposal or some other continuous proposal, as long as it's symmetric, and then your proposed value x prime comes up, and then you just compare the probability. Is the probability of the proposed value greater or less than my current value? If it's greater, then our ratio is going to be greater than 1, and so our acceptance rate will be equal to 1. We're going to go for sure. If the proposed value has a lower probability, then our ratio will be smaller than 1, and we'll go with a probability only equal to that ratio. Is this okay? And then, all right, so if we accept, then x at time k plus 1 will be equal to our proposed value. Okay, then x at time k plus 1 will be our proposed value. Otherwise, we reject, and x at time k plus 1 will be equal to our current xk. Will be equal to our current xk value. Okay, is that all right? So let's try this out. So I'll do this, and we'll say, let's say our target distribution is the normal with mean equal to 10 and standard deviation equal to 2. Okay, so this is our target thing. Okay, so our target PDF will be equal to, if we did this in well, let's see, our target PDF, let me close our attendance poll. I always forget to do that. Okay, let's look up Wikipedia normal distribution. Okay, so I got 1 over 2 pi sigma squared. Okay, so it's, I got, okay, so I got 1 over root 2 pi, and then sigma squared I'll just write exp of minus x minus mu squared over 2 sigma squared. Okay, but in our case, we could just say f of x is equal to what? D norm of x, mean equal to 10, and standard deviation equal to 2, right? So this is what we have. This will be our what we will use to calculate our acceptance ratios. Okay, All right, and then let's, for our proposal, let's just say we will use a random normal with mean equal to our current xk and standard deviation equal to 1. All right, and so what this means is in R, we will use our norm to propose one random value. Okay, and so we will do our norm 1, comma, and we're going to set the mean equal to our current xk value, and I just arbitrarily chose standard deviation equal to 1. So this basically takes our current xk value, it centers a normal distribution there, and it's going to propose one random value drawn from this normal distribution centered at xk. All right, and then we calculate a ratio. The ratio will be the minimum between 1 and then we'll do d norm, or basically of my x proposed divided by the x current. Okay, where f of x is equal to basically the PDF of the normal with mu equal to 10 and standard deviation equal to 2, or d norm x 10 2. Okay, and then we draw a u random uniform from 0 to 1, and then we will accept x proposed if u is less than the ratio. Does that make sense? Is everyone following this? Some of you guys are nodding your heads, and then others of you I'm not quite sure, but well, all right. Well, let's do this, okay? Okay, so I've already written a lot of this out. Okay, so we'll say P is our target density. I guess in our slides I wrote F, but we'll say P is our target density. P is going to be a function of x where all I'm doing is I'm just plugging in the value x, and it's going to spit back whatever the normal density is with mean equal to 10 and standard deviation equal to 2. Okay, so if I say this, then we could see what's P at 10, and it's 0.199. Okay, and then values bigger than that is much smaller. Things like that, right? Okay, because it's symmetric and stuff. Okay, Q is going to be our proposal distribution, and we will propose values from a normal which is centered at our current xk, and has a standard deviation of 1. Okay, so QR needs to return a proposed value, and we provide the current value. So QR is going to be a function of our current value xk, and it's going to be our norm, so it's returning one random value. Our norm returns a random value where the mean is equal to xk and standard deviation is equal to 1. Right? So if I call QR on 100, what would it return? About. it'll return a value, a random normal value centered at 100. So it might return anything from like 98 to 102, maybe 97 to 103, but most likely a value between 98 and 102, okay? So we get a value like 100.015, or we get 99.74. If I call QR on the value 7, then it'll return a value probably between 6 and 8, almost surely between 3 and 9, okay? And we get 6.95. So QR is it just takes in your current value and it says, all right, if we have a random normal centered here and I draw one random value, what's that random value? So this is just, it proposes a value centered there. Is that okay? So that's our proposal distribution. Okay, I'm going to store my values here. We'll do 10 to the 5. We'll say, or we'll just do 10 to the 4. Okay. And I'm going to purposely start off at a terrible location at xk equal to -40. Okay, remember our target distribution has a mean of 10 and a standard deviation of 2, which means like 95% of my values should be between 2 standard deviations below and 2 standard deviations above. So 95% of my values should go from 6 to 14, and almost 100% of my values should go from 4 to 16, right? And then so I would never get a value like -40, okay? But I'm purposely going to start off in this terrible location of -40. And then watch what we do. Okay, so this is the entire algorithm. We start off, my proposed value, x prime, is going to be whatever QR, my Q random value returns if I'm centered at xk. Okay, so this is x prime. This is we propose a value. Then I calculate my ratio. My ratio is going to be, remember, this is the PDF of my normal distribution. So we're going to calculate the PDF at x prime, and we're going to calculate the PDF at my current value xk. And I take the ratio between those two, and I'm going to take the minimum between 1 and that thing. So just in case, I mean, with the computer, I can just leave it and ignore it. But basically, if this is bigger than 1, ratio will be equal to 1. And if this thing is smaller than 1, then it will be whatever this ratio is. Okay? And then I'm going to accept it. I'm going to take a random uniform value, just one random uniform, and I will accept it if that value is smaller than the ratio. Okay? So accept will be a true false value. Right? All right? And then I have an if else. So if I accept it, then the value that goes into stored will be x prime. And if I reject it, then the value that goes into stored will be xk, my current xk value. And then I update xk with whatever I stored into position I. All right. Does this make sense? Okay, so this just follows the steps of the Metropolis algorithm. So I'm starting off with this terrible xk is -40, and then I run my loop, okay, and then it's done. All right. Let's just plot and let's just see what this looks like. So let's look at the first 1,000 values of stored. All right, and this is what we see, is that basically in the beginning I'm starting off at -40, and if I propose a terrible value, remember, the region that we want is around 10, from like 6 to 14-ish or something like that, okay? If I start off at -40 and I propose like -41, then the ratio of -41 versus -40 is going to be small, and I won't accept it. And so what you see is that in the beginning, I'm pretty much only moving towards the area of a higher probability, okay? I might propose some bad values, and maybe on rare occasions, I'll accept it and dip a little bit away, but most of the time, I'm moving closer towards the area of higher probability, and then once I get into this region of high probability, then I spend most of my time hanging out here. So once I get to that region of high probability, then it's kind of a random walk in this area. And so if I plot the next 1,000 values, 1001 to 2000, okay, now we just kind of have a random walk in the zone that we expect, which is centered at 10 and going from -4 to going from 4 to about 16-ish, okay? And we can ask, all right, let's look at a histogram of our stored values. Okay, and what we see is if I just take all the stored values, we have this very long left tail, and that's because in the beginning, until it spent a lot of time in this region of very low probability, right? Because if I were to plot the density, I need to make a sequence S from -40 to 20. Phi equals 0.0112. Well, I don't know. Okay, well anyway. And we'll plot S versus, okay, well, let me just make the histogram. Okay, so if I cut off maybe like the first 1,000 values and just do from 2001 to 10,000 and do bins equals 30. Okay, this looks a lot like, or breaks, I got Python mode. Breaks equals 30. This looks a lot like the normal distribution, okay? Centered at 10 with a standard deviation of 2, okay? Whereas before, if I use the whole thing, we're including kind of that beginning phase where we had a whole bunch of bad values, okay? So that's the thing with Markov chain Monte Carlo is there's kind of this burn-in period where you might start off in a location of low probability and you're just kind of searching around, moving slowly towards the area of higher probability, and then once you're in that area of higher probability, you're spending most of your time there. So you've got to throw away that beginning time where you're just kind of like searching this barren wasteland of near zero probabilities, and then once you get to the region of interest, you'll spend most of your time there, and then you'll get your values there. Okay, we'll stop here, and we'll take a look at some more on Wednesday, and see you guys then.